Why are some materials covered in crystals while others aren't? And how do solar panels even work? Let's find out. Solar panels convert light into electricity. They're photovoltaic, which means light, photo, and voltage, voltaic. When light, sunlight or artificial hits a solar cell, it generates electricity. The stronger the light, the more power is produced. Interestingly, this process can be reversed. Connect a solar cell to a power supply, and it emits infrared light, invisible to the eye, but visible to a camera without a filter. This happens because light is made of photons. When a photon hits a solar cell, it knocks an electron loose, leaving behind a hole. This is the photovoltaic effect. The electron is pulled up, the hole drifts down. If we connect the two with a wire, electrons flow through it, powering devices like LEDs, which then emit light. So can an LED power itself? Think about that. Solar cells are everywhere, from calculators to rooftops and even massive solar farms. A solar module is made from multiple solar cells. A string is multiple modules. An array is multiple strings. Inside a basic solar cell, we have a metal plate, which acts as the positive electrode. Then there are silicon layers, one doped with boron and one with phosphorus. The PN junction is where the magic happens. Additionally, there's a metal grid serving as the negative electrode and a glass cover to protect the fragile cell. Electrons flow along tiny metal fingers into bus bars and out to the circuit. But since silicon reflects light, we use an anti-reflective coating and roughen the surface to capture more light. Each cell only produces half a volt, so we connect many in series for higher voltage. A solar panel is built layer by layer: a backsheet, EVA adhesive, solar cells, glass, and a frame. EVA protects against moisture and shock. The way we connect cells, in series or parallel, affects voltage and current. For example, 4 panels in series equal more voltage. 4 panels in parallel equal more current. But both can produce the same wattage. To store energy, we need batteries and charge controllers, which prevent overcharging and allow us to use stored energy at night. This simple solar fan spins faster with more sunlight, but doesn't work at night, unless connected to a battery. In off-grid systems, the solar panel charges the battery during the day, and a controller manages power to devices and prevents backflow. For grid-tied systems, solar panels connect to an inverter, which converts DC, or direct current, into AC, or alternating current, the type used in homes. During the day, if the panels produce more than you use, excess energy goes back to the grid, a system called net metering. Advanced systems include battery banks. During a blackout, the battery powers the home. Solar farms scale this up massively, feeding high-voltage electricity to the grid via substations. But the sun moves. Solar panels work best when facing it directly. This is why we calculate the optimal tilt and direction, and use tools like PV design software to simulate installations and avoid shading. Now, let's talk about solar cell types. Polycrystalline, which has blue flakes, is cheaper and has an efficiency between 13 to 17%. Monocrystalline, which is black, is more efficient, ranging from 15 to 19%, but it's also more expensive. Then there's thin film, which is flexible and low cost, with an efficiency of about 5 to 8%. They all use silicon, refined from silica sand and carbon, melted, purified, and sliced into wafers. In polycrystalline, many silicon crystals form. In monocrystalline, a seed crystal forms a single crystal structure, more efficient, less waste. Thin films are cheaper but degrade faster. Light energy comes in waves, and only certain wavelengths can free electrons in silicon. Those above 1.1 electron volts or below approximately 1,127 nanometers wavelength. Longer wavelengths, like infrared, don't generate electricity. Others produce excess heat, reducing efficiency. Plus, light is reflected, some blocked by dust, and energy is lost in wires and inverters. That's why solar panel efficiency tops out around 30% under ideal conditions. So back to the earlier question, can an LED power itself? No. While the LED emits photons, the conversion back into electricity is inefficient. You'd need around 10 LEDs to power one LED. A solar cell is like an LED working in reverse. Let's wrap with the science behind the PN junction. Phosphorus adds free electrons, which we call N-type boron creates holes, known as P-type at the junction. A depletion region forms. An electric field builds light. Hitting this region knocks electrons free. They're pulled toward the N-type while holes drift to the P-type, creating voltage. Provide a wire and electrons flow to the other side to recombine with holes. That's your current DC electricity. And that is how a solar cell works.